Hello everyone, we're back with another video. Here we'll talk about magnetism. Let's deal with some few terminologies. The first one is the pole of a magnet. Let's assume what we have on the screen is a magnet with north and south poles. The magnetic force in a magnet is strong, or strongest as the case may be, at the poles. So strongest at the north pole, and then also strongest at the south poles. The effect is felt more at the poles than at any other point in the magnet. The second terminology we'll have to deal with here are permanent magnets. You have some magnets that they depend on whether you put them in a magnetic field or not. But for permanent magnets, what they do is they produce their own magnetic field. Like what you have on the screen, the magnetic field is from the magnet. Those are permanent magnets. And then we've got induced magnets. There are different breed of magnets or type of magnets as the case may be. What they do or how they work is that when you place them close to a magnetic field, they act like magnets. Take them away from magnetic fields, they're just normal materials. So for example, this is a box, just saying, and then you place this box in this particular magnetic field, and then it will start, the box will start picking up iron nails or needles as the case may be. But once you remove it from the magnetic field of this particular bar magnet, it will stop attracting. For permanent magnets, they can attract and repel since they have north and south poles. In this, magnets can only attract. Just for you to keep that in mind. Yeah, magnetism is a type of non-contact force. Non-contact force. When we say non-contact force, there are forces that it's not most for those objects to touch each other before the force can be felt. The objects just need to be in each other's field, and then we'll feel the effect of that force. An example of that is electrostatic force, gravity, and then you've got magnetism. For this three, they're non-contact forces. All right, and then you've got electric fields as well. Electric fields as well. So it's not most for those objects to be in contact. Now let's now talk about how like poles and non-like poles, how they behave. Let's say you've got a magnet. A magnet will always have a south pole and a north pole. And then you've got another one here, north and south. Because they're like poles, they'll repel each other. They'll repel. Alright. And then at this point, that's where you have like the neutral area where the magnetic field lines are not touching. So if you've got like poles facing each other, like poles repel. And the same thing happens even if it's south-south. So let's say we'll flip this. We make this north, we make this south, we make this south, we make this north. Same thing is going to happen since they're like poles. But if they're not like poles, let's say they're opposite poles, how will these guys behave? Let's take a look. If they're opposite poles, let's just make this opposite. If they're opposite poles, definitely they'll attract. they would attract. So you have the field lines like this. So definitely they would attract. So opposite poles attract. Like poles repel, opposite poles attract. Now, when we talk of magnetic materials, that means we have some materials that are susceptible to magnets, to magnetic fields. In fact, when you have them around magnets or in the magnetic fields, they'll easily respond to whatever experiment you're trying to perform, and then even turning some of them into magnets. Quite easy. What are those materials? You've got iron, you've got steel. Now you have this, guys, iron and steel. That's the first step, because steel is an alloy made from iron. All right, and then you've got nickel. Lastly, you have cobalt. All right. Now, for this four now, is either you have them as magnets or magnetic materials. So in this case, let's say they're magnetic materials, they tend to become magnetized easily when you compare that to any other material you have on ground. All right. So in a magnetic field, the strength of the magnet is not equal. Yeah, the strength of the magnet is not equal. The strength of the magnet is actually dependent on how close the object of the magnetic material is from the magnet. So for example, let's say you've got a magnet here, and then you have a pin, and then you have a pin far away. Let's say this is 10 centimeters away. And then you have a second scenario, the same magnet, and then you have a pin very close to it. Let's say this is 2 cm. The effect of the magnet will be felt differently here. Let's say this is A, this is B. For A, the object is close to the poles, so the effect is more when it comes to the strength. But for B, the pin is quite far, so the effect would not be that strong. So you can see how distance plays a huge role in this. And then the direction of the magnetic field at any point is given by the direction of the force that will act on another north pole placed at that point. Now, what I said earlier, it means that when you have the field lines, what you have on the screen here, that's what we term the field lines. The magnetic field lines, they have a direction. You can see the arrows, those tiny little arrows. You can see the direction. It shows the direction of the force. That's the magnetic force. So the direction is always from the north. That's the north second pole to the south second pole. For example, let's say we have a compass right here. How did we even come about the direction in the first place? Let's say you place a compass here. Your compass will point in the south direction. So if you want to know the direction, what you just do is just to place a compass around a bar magnet, and then you would see the compass point towards, just follow the lines and you get that. Same thing here, all the way down. So if you're not sure in a magnet as to the direction of the magnetic field lines, all you have to do is just place a compass near it, and then the direction of the compass will show you the shape and the direction of the field lines. Now, the way the compass works, it responds to the magnetic field of the earth. So what you have here, that's the Earth's magnetic field. So it responds to the magnetic field of the Earth. So the needle in a compass, it contains a little tiny burr magnet, and then the compass will point in the direction of the Earth's magnetic field. So the direction of the compass actually led us into believing that the Earth's magnetic field originated from the movement of the Earth core. In the core of the Earth, you've got iron there, and then the iron is kind of molten in a way, and it flows. So we believe that's where the origin actually came from. That's the origin of the magnetic field.